some further simulations for fluid mechanics. We work a lot in combustion, in external aerodynamics, especially large eddy simulation. And also we have some bio applications, in this case, the respiratory system. So, well, regarding the formulation for the incompressible flow, we have undergone a huge transformation in these last 4 years, I would say. Before, we were using what is typically the most used approach within the finite element community for fluid mechanics. This is the variational multiscale method and an implicit treatment of the momentum equation. Variational multiscale method is a stabilization technique that gathers the most advanced stabilization technique for finite elements. And now we have switched to, I would say, like more standard approach within the general fluid community. We use a formulation where we use pure Galerkin discretization. This means we do not introduce any stabilization. For the convective term, we use a very recent formulation that is called EMA. It not only conserves energy, but also momentum and angular momentum. This is very nice for the formulation. We typically use equal order elements for both velocity and pressure, typical linear elements, but can also use higher order elements. Equal order elements that do not satisfy the in-sub condition, we need to stabilize this, and for this we use the fractional step method. This is the only stabilization that we use, but this is quite common, the use of the fractional step method. For turbulence model, we use explicit schemes, contrary to what we did before, where we use implicit LES. Now we use explicit method for turbulence modeling. Our preferred scheme is the Breman model. We also use sometimes Whale, and we are working with Professor Ugo Piomelli on the extension of the ILSA method he's developing to unstructured grids. That is where we have the biggest expertise. What we really like about this new formulation is that it is simple, just pure Galerkin together with a fractional step. I guess we cannot do it simpler than this, much simpler than what we did before. And we do not have any numerical parameters, stabilization parameters to tune. I am very, very happy about this. So we can also use higher order elements, quadratic, and we have tested some cubic finite elements. We do some very nice results. I will show some small results. For the mass matrix, we are using an explicit discretization of the momentum equation. We have used an approximation of the consistent mass matrix proposed by Germont that gives us better results than the use of the lumped mass matrix. For the temperature equation, we use an entropy viscosity method, also proposed by Germont. And finally, within this project, we are trying to do some small progress into a fluid structure interaction. So we want to simulate the rotating wind turbine and also the deformation of the blades, at least give some advances in this direction. For solids, we will use continuum shell elements for anisotropic laminates. And here we have found that the key challenge is the generation of the mesh and also obtaining the properties of this mesh. There is very little information in the literature. For the meshing, we use ANSA. This is a commercial mesh generator, both for solids and also for fluids. We are very happy with this commercial measure. And finally, for the solids problem within EoCoE, we are introducing the use of MAMPs as a direct solver instead of iterative solvers that we used before. So some results for the basic problems. Here we want to show that or to prove that our code introduces very little numerical dissipation. This is very important to have an accurate large eddy simulation. So this is the well-known Taylor green vortex at Reynolds 1600. On the top, we show results for linear elements of the total kinetic energy and the total entropy for 3 different meshes. This is the evolution in time. In the right, you can see the different figures of how the flow evolves. And well, I haven't introduced comparison with other codes, but there is a very nice review paper by Professor Charles Moulinex, where he has compared several low-order methods and high-order methods for these problems. Within the low-order methods, that is unstructured grids, that are the ones that are more comparable to us, we can say that we have much better results, at least to the codes he used, that were OpenFOAM and Code Saturn. Our dissipation is much lower. And moreover, compared to typical finite volume schemes, we can also go to at least third order in space by using quadratic elements. And we see also very, very nice results when we do this. For a more complex case, perhaps one of the most complex cases that we have run, this is the CRM model. This has been run by Oriol Lemkul, the head of the CFD group at Barcelona Supercomputing Center. This is at the Stanford CTR summer program led by Professor Moyne. And these are one of the best results that exist for world model FES over complex geometry. You can see that we predict the lift and drag very well for this high angle of attack. One thing that I would like to remark about this formulation is that we use the same formulation. We don't have any parameters to play around with, be it on a full airplane or be it on a very simple cube or a 2.5 D geometry of a wind turbine blade. Regarding wind energy, we started with wind energy in a collaboration with Iberdrola. This was quite strange. Typically, one starts first in research and then gets in contact with a company. We had this luck that one of the bosses of Barcelona Supercomputing Center got in touch with one of the bosses of Iberdrola. They were playing tennis and they said, perhaps we can do something together. And well, this was luck for us. Well, we have been working hard for these last 8 years, and we started with Iberdrola, but now we have been in several European programs, projects, among them the new European with Atlas, for example. And well, we have adapted Alya for the simulation of wind energy. Here we show some results. This is a wind farm from Iberdrola. And we have represented the wind turbines with actuator disks. These are some other results that we typically present to Iberdrola. We have adapted our code so they can use it. We have generated pre- and post-processing tools. Here we show our results plotted on Google Earth, and this is very comfortable for them to see the results. So this adaptation that we have done for Iberdrola, we have Alya that runs in the Mare Nostrum supercomputing supercomputer. And we have developed special tools, small programs, so that they can start with their topography, the roughness. In this case, we generate the mesh directly ourselves, so with very little input parameters, what they typically give to a commercial code. We generate a mesh. Then we generate the boundary conditions. Here we need the latitude, the geostrophic wind, and a couple of other small data. And with this, they can submit the run. They typically they have access to Mare Nostrum, and they do the simulations themselves. When they have problems, they contact us, and we give them support. Finally, we have developed some post-processing tools where they can see the results easily in the format that is comfortable for them. Well, Towards exascale for energy, you all know that we are in an intersection of two revolutions, a revolution in energy going to carbon neutral energies, and moreover, there is a revolution in computational hardware. The machines cannot continue growing with the same paradigm. They would consume too much energy. And well, here is where EoCoE is positioned. EoCoE is one of the, I believe, 8 or 10, I don't know how many centers of excellence there are now in the European community. These are projects that are focused in going towards exascale. EoCoE is focused on energy, but well, several energies. One of them is wind. That is the one I will talk about here, but we also have people working on meteorology. This is mesoscale models applied to wind, but also to solar energy. But these are people that work with WRF mainly and these kind of codes. We work on microscale modeling. Then there are people working on materials for solar cells, for supercapacitors, people on water for geothermal energy and also for the dams. And finally, there is a group working on fusion. The project is formed by 18 partners. Most of them are from Germany and France. So regarding wind energy, which are our targets? What do we want to simulate? We want to simulate large eddy simulation over complex terrain. We have an unstructured code, and this is where we can compete, not on flat cases. And moreover, we want to introduce full rotor simulations. This is introduce the real wind turbines, not using actuator disk or actuator line models, but actually simulating the blades and their rotation. In the end, the objective would be to couple these two things together and be able to simulate a real wind farm with the real wind turbines. This would allow to advance the understanding of the flow physics and the behavior of the whole wind plant. So our ambition is to try to make Alya an open source code for the wind community, a code that could be used by the wind community. It is very difficult to go to the exascale. Not all codes will be able to go to exascale machines or to be able to use them efficiently, at least in the medium or short term. In this way, Alya should be kind of an alternative to SOFA, that is the most established open source code for wind. And actually, Tunalu, that will be its replacement. It is currently being developed in the US as a replacement to SOFA. So we hope that we can somehow compete with these codes. We are targeting simulations of 10 to the 10 or 10 to the 11 grid points by the end of the project at the end of 2021. Within EoCoE, there is another code that is being developed for wind. This is not, I do not participate in this code. This is a lattice-Boltzmann code with structured grids that is being developed by Ulrich Rude and his team at Erlangen University and Surfax. The objectives are to optimize the position of the wind turbines, to increase power output, to reduce wind turbine maintenance, and to improve the competitiveness of wind energy by reducing its cost. So, well, you all know that in wind energy there are a wide range of temporal and spatial scales. We start mainly at the micro scale, that is simulating the wind farm, but we want to go towards full rotor simulation, that is smaller scales and better resolution of the wind turbine. And moreover, we want to have some coupling to the mesoscale, because we know that there are cases where you cannot reproduce the observed results if you do not include coupling with the mesoscale. So what do we need for all of this, or what do we have for all of this? We want to deal with complex terrain. We use unstructured grid. This is a key point for us. We need to introduce Coriolis forces to simulate the atmospheric boundary layer. We obviously also need to introduce temperature coupling. We need a caping inversion for the Coriolis force, and moreover, we are interested in stable and unstable situations. When we have introduced temperature coupling, this is by the Boussinesq force. We see that these gravity forces introduce some problems when we want to couple this with a fractional step method, and we have been working recently on this, and we already have a solution. We also want to we also have the possibility of introducing the forest. We have a canopy model. We can introduce actuator disks. And moreover, we have been actively, and we are actively working on wall model LES. This is for us key to have a good simulation. And on the other hand, and perhaps not within EoCoE, but within another project that is called EnergyCo, we are working on the coupling with the mesoscale. Here I will present some results about Bolund and some very interesting observations. The Bolund experiment is perhaps one of the best known cases for complex geometry, complex 3D flow. The geometry is not that complex, but it gives rise to a very complex 3D flow. And it is one of the cases that has been most studied by the wind energy community. This cliff is quite low, just 12 meters, so you do not need to introduce Coriolis forces, nor thermal coupling. This is an advantage so that you can at least benchmark a small part of your code and know that this part is correct before going to all of the complexity of the problem. Moreover, the inflow is quite simple because it comes from the sea, and this is also an advantage of this problem as a benchmark. So this is the mesh that we have used. I want to show that it's a unstructured grid, and we have refined a lot in the region of importance where you have the cliff and you want to resolve this. For this mesh, we use 5.7 million nodes, quite a small mesh. We also later used a refinement to have a much finer grid. And this case runs in 960 cores in 2 days. So we have tested two options for the inflow, a synthetic inflow proposed by Kempf and coworkers. And we have also tested the possibility of a precursor run, periodic flow over flat terrain. We didn't observe significant difference between these two options. Here are the results for the mean error. There is for this case, there is a very well quantified comparison. And these are results from the original benchmark and then from some other papers and the results for Alya. Want to see that the results for Alya are comparable to other results. Good, I would say. But then there is something that is more important. We have come across this paper for wind turbines in complex terrain. The devil is in the details. And this was very interesting to me. This is an experimental paper. These are people from Denmark that were doing wind tunnel experiments with the Bolund geometry. So they were working in a wind tunnel. They had produced a scale version of the Bolund geometry, and they were running, well, I wouldn't say not running because this is experimental. They were working in the wind tunnel, and then they realized that the geometry was not that accurate. It was quite smooth at the top of the hill. So they decided to kind of improve it by hand. They added some clay to obtain something that is shown here in figure B. that is more similar to the actual geometry that they had seen in person. And on the right, you can see the two results. These are experimental measurements in the wind tunnel. And you can see that there is a huge difference. The position here of this wind turbine represents the region where the velocities were compared. These are the experiment where the experimental data was taken. So, well, this was very interesting to me. I didn't continue working on Bolund. I tried to get a better geometry, but I haven't been able to do so. At least to my knowledge, there is no corrected geometry available for the community. Well, I believe that this would be really important to continue working on this case. It seems that instead the communities has moved over to more complex cases like Hornamosen, Alya, Perdigao. But well, here you have a lot of phenomena working together. You have the canopy, you have Coriolis forces, the thermal coupling, the effects of the boundary conditions, the coupling of the mesoscale. So, well, I would prefer to be able at least to have a good geometry of Bolund to at least be able to validate my case on a simpler case. Here are some results from the Hornamosen problem. This is here I haven't included Coriolis forces, but at least they are some preliminary results. This mesh was around 240 million elements. Now I will step over to the full rotor model. What one needs here is to have a domain where most of the domain is a fixed mesh, but then around the blades one has a rotating mesh that moves with the wind turbines. We have developed this sliding mesh approach in our parallel code. This has been quite a challenging development, and we can now obtain some nice results, and we are currently working on the comparison of these results against the experimental data. We have obtained a support letter for EoCoE from Vestas, and we hope that at the end of the project we can show them something that could be of their interest. Here we can see some further results. The part of the mesh that is rotating is just a small region around the blades, a disk around the blades. And we see no numerical artifacts at the interface. This is very good. Regarding the HPC aspect of the project, here I show the different areas that we have in EoCoE. We are wind, the one in yellow, and our interaction will be mainly on programming models. This is improving Alya, and also on scalable solvers, linear algebra packages. The objective of EoCoE, as set up by the European Commission, is to have an 80% of effort in HPC and just a 20% of effort in the scientific challenge. This is hard because there are lots of things to be understood on the scientific part, but we follow what we were told to do. So regarding programming models, we have been working on porting to GPUs. Co-execution, that means using the CPU and the GPU at the same time. On fast and scalable mesh partitioning using space filling curve. Dynamic load balancing. We also have this coupling for the full rotor simulations for the rotating part of the mesh and a fixed mesh. We are working in collaboration with George Heyer and his group within EoCoE for node level optimization. We also have support from the POP Center of Excellence, and we have done some work in going towards very huge meshes. So regarding the GPU implementation, a finite element code has two main parts: creation of a matrix and solution of a linear system. We will concentrate on the creation of the matrix. For the solution of the linear system, we prefer to use external packages provided within EoCoE instead of Alya's own solvers. So what we have done is an approach using OpenACC. This we started at the EuroHack hackathon in Lugano in 2017. And the idea, when you have a finite element program, you have a loop over all of the elements. And now we work over a group of elements, and the size of this group is this vector size. So we do several elements at a time. This has been an advantage not only for the GPU, but also in the CPU case. In the CPU case, we have found that working with 8 or 16 elements at a time gives an advantage in CPU time. I believe that we were able to reduce the CPU time at least 50%. Here we have some results in PISDAME, the Swiss supercomputer. On the left, we can see the results only using the CPU. We can see that with 2 nodes, that is 24 cores, we took 3 seconds for a certain simulation. And we compare this against what we can obtain with 2 nodes, that is 24 CPUs plus 2 GPUs in the same machine, compiled with PGI compiler. And there we played around with this vector size, how many elements we send at a time. We found that the optimum number was 128,000. And for that case, we get 1.6 seconds. That is, we go nearly twice as fast. This is the results we obtained at the time. We have been working a bit on this. I prefer to present this because here is where I was deeply involved. But our results are currently more or less similar to these ones. I also want to talk about co-execution. So when one uses a GPU computer is not just GPUs, but you need also the CPUs. And the typical approach is to let the CPUs idle, to use them just at the beginning of the run to read the data and to do some output work. But all of the work is done by the GPUs. Instead, we are also testing this co-execution where we give some works to the GPU, most of the works to the GPU, but also some works to the CPU. In order to do this, we use this dynamic load balancing approach that we have that allows us to give a lot of work to the GPUs and smaller work to the CPUs so that they are well synchronized. Well, we have been able to save around 50% of time by working with this co-execution approach. That is, the CPU takes care of 15% of the work for free, I would say. So here is the dynamic load balancing that we use. It depends on this space filling curve. That is a partitioning method that is very fast and can be done in parallel. So one starts with one initial partition that one has decided, and one sees that one of the subdomains, the one that takes the most time, takes around 6 seconds, while the one that is faster is taking 3 seconds and is waiting for another 3 seconds. One sets some weights on the elements based on this data and repartitions. After repeating this several times, in this case 18 times, one has obtained a very, very good balancing. In the case of GPUs, well, the GPUs have a much bigger load than the CPUs, but everything works in a very well synchronized way. For the dynamic coupling, well, we have been working a lot in this. I won't go into the details. I want to say that we are using it not only for the wind turbines, but we have been able to simulate a real car for SEAT, the car company, with rotating wheels. Regarding node level optimization, as I mentioned before, we are working with George Hager and his group from Erlangen University. He develops Liquid. And we are currently analyzing Alya with this tool. And we have already identified some points, and we think that at least we should be able to improve our speed by 20, perhaps 30%. We are also working with the FOP, Center of Excellence. I want to mention that we work mainly on the assembly of the matrix, as I mentioned before, for the linear algebra part, for the solution of the system, in this case the pressure, because we are working with an explicit solution for the momentum. We prefer to resort to external solvers because we have found that they are faster than what we had in Alya. I want to mention that already in EoCoE 1, that was the previous version of EoCoE, we are now in EoCoE 2. By using mainly Intel tools, the Intel Inspector, we were able to reduce the time for the assembly of the matrix by 30%, and we hope that now we can get a further 20 or 30%. Regarding going towards the exascale, very huge meshes, for unstructured meshes, 10 to the 10 or 10 to the 11, this is a real simulation. We have got access to Mare Nostrum, nearly the whole Mare Nostrum, 100,000 cores, and we were able to perform a 24-hour run. This is not just a test, it's a real run in this CRM model with 2 billion elements. Finally, I will talk a little bit about iterative solvers. We have coupled Alya. We have a very nice group of people working on linear algebra within EoCoE. We have coupled Alya to AGMG. This is a multi-grid solver developed in Belgium by Ivan Notey, and also more recently to PS Blast MLD2P4. This is another multi-grid, multi-level iterative solver. This one can work not only in CPUs, but also in GPUs. And we have found that it has a better scalability. We have also interfaced with Mafis, a code developed in INRIA, and we're doing some preliminary testing. For direct solvers, we are working mainly with MAMPs, and this is for the solids problem. I present here some of the results that we have obtained both with AGMG and PS Blast. This is kind of a strong plus weak scalability. So we use the mesh for Bolund, 6.6 million unknowns. And we use this mesh multiplication tool we have in Alya that divides the elements into elements that are half the size. So you have 8 times more elements and nodes in 3D. You go to this group, this new mesh with 45 million nodes, and you can apply this recursively. We did it a second time and went to 350 million nodes and more than 1 billion elements. Here we show the results for the number of iterations. First, this is what the solver people are very interested in. I am more interested in the CPU time that I will show later. And we can see that we have a very nice algorithmic scalability, at least from 0 divisions to 2 divisions. The behavior is very nice. When you apply 1 divisor, the number of iteration rises a bit. Then one could debate about how fair this weak scalability is. When you have a complex geometry, when you have a very simple geometry, it's easier. But when you have a complex geometry, the problem is kind of changing. So, well, these are the observations I did before. Some very nice algorithmic scalability. I want to mention that we use a fixed CFL, so actually the time step is being reduced when we refine the mesh, but we haven't observed a significant dependence of the number of iterations on the time step size. Regarding the CPU times, here we have the CPU times. could look at the case for 48 cores. If we want to look at the weak scalability, we can look at 48 cores, 384 cores. So this is 8 times more cores, and 3072. This is the case where we are working with around 100,000 unknowns per node. And we see that we have a very acceptable scalability, both with HGMG and PS Blast. When we push, we reduce the number of unknowns per core even further. This is, for example, the case of 192, 1,500, and 12,000 cores. We see that PS Blast still copes quite well, not perfectly, but quite well. But on the other hand, HGMG, especially in the case in the finer mesh, it does not scale. It does not have strong scaling, and then the weak scaling is also ruined. So, well, these are the results I have kind of explained easily while looking at the results. For 100 unknowns, both solvers work well. And if one wants to work with less unknowns per core, clearly PS Blast is a much better option. Something I want to mention, these are results we have done on Mare Nostrum. We ran for 20 time steps. And in the previous results, I have presented the minimum time of these 20 time steps. Why did I do this? Because we observed that at some specific time steps, we have a lot of noise. The time rises like 10 times. And this is not a problem that we are doing more iterations. The number of iterations are the same. This is a problem of Mare Nostrum hardware or its software or whatever. This appears when one goes to a big number of cores, but it seems that at some points Mare Nostrum communication starts working poorly. And this is not a problem of Alya. Here we see that the steps that take a lot of time are around the step 15. And if we run this again, they could be at any other point. Well, the solution that we have found is to use the minimum of the 20 time steps for comparison. This is something that the people from Mare Nostrum are working on, and this obviously will get more complicated when they go to the real exascale. Well, the benefits, I know you all can guess the benefits of doing this, getting a much better understanding of the flow in the whole wind farm and also around the wind turbine, reducing maintenance cost, improving the amount of energy you can get from the wind farm, and well, somehow complementing the fidelity gaps that you have in field experiments, where the things that you can measure are quite limited. We hope that this can help reduce the cost of energy. It has been estimated that it is currently at around 5 cents per kilowatt hour, but it could be lowered to 2 cents. Moreover, similar research, especially the full rotor research, would help understand noise production and reduce it. Finally, the challenges that we find, or some of the challenges we find, are on validation. We believe that the cases are getting too complex and that simple cases have not been looked into well enough. And then our other bigger challenge is that the objective of EoCoE is to develop Alya so that it can be used by the wind community as an alternative to Nalu. That is the replacement of SOFA, the most used open source wind code. I have been talking with Michael Sprague, the leader of the Nalu code, and also of 2 projects around this code that are Exawind, that is more related to the HPC part, and also atmosphere to electrons. That is more related to the physical part, to the modeling, and to the validation. And when you look at the numbers, it is very hard because the budget, this is one of the first figures he showed me, and his budget is $2.5 million for the atmosphere to electrons project per year, and 3.5 to the ExaWIN. This is a total of $6 million per year, and this is more than 10 times that what we have for wind in EoCoE. So, well, we will try to do the best that we can, and well, we hope that we can obtain something that is at least comparable. Well, I leave you this very nice visualization of the results over the Bolund hill, despite I have already told you that well, the results do not have much use because the geometry that we use, that is the one that is available, is not very realistic. Well, thank you, and thanks for the European Commission for the support they are giving us to do this work.
Thank you very much, Hubert, for a very interesting talk, and yeah, learned a lot about the EoCoE project there. I wonder if people have questions. So far, nothing in the chat. If you have a question, please write it in the chat or raise your hand using the raised hand option. In the meantime, I have a question for you whilst maybe some more questions come in. I was wondering about this point you raised about the validation, particularly like the full-scale validation. What is the, what can be done about that? I mean, there are the Gables cases could be interesting to use for validation of the atmospheric boundary layer over like the course of a day. We've been using that a bit, but it could also be to perhaps look at the Pedagao data where there was an intensive measurement campaign that could be also used. We're thinking of we're going to use it in the HPCWE project. It could be a case to use a bit like the Bolund case where many modeling teams sort of went to the same task. Do you have any thoughts about that?
Well, my thoughts are that about Gables, I understand it's a flat case, and well, it's a very good.
Oh, you froze. Was that just me, or Hubert has frozen?
Yeah, he has frozen.
Oh no, he's come back again. Yeah, you're back again, Hubert, I think.
Ah, sorry.
You froze for a second there. You were just answering about the flat cases.
Well, the flat cases are not the key of our interest. It's useful to validate that our code is correct.
Please, if you're not speaking, and it's only Hubert speaking now,
there is some noise.
Yeah. Everyone needs to mute unless speaking, and there's only Hubert speaking.
For the flat cases, Gables seems good, and there could be other options. But as I said initially, our code is an unstructured code.
Okay, Hubert's frozen again. It's interesting. Maybe it's the animation.
I will shut down the animation.
Yeah.
Okay.
Yeah.
So for the flat case, you have Gables, and there are other alternatives. There is this Swift case that is from the US, and there are other options. For the complex cases, yeah, what I see is that we are moving towards Perdigão. We also will simulate Perdigão, but what I see is that here you have a lot of different phenomena coupled together. And for really validating, I would prefer to at least be able to validate my LES part in a neutral case without Coriolis, then add Coriolis and see what happens. And this is what I was highlighting. The Bolund case for me would be an excellent case. I have even read a recent article by Matt Chartfield where they talk about the cases that they will be using in this atmosphere to electrons project. And he mentions Bolund. I still want to talk with Michael Sprague or Matt Churchfield to try to understand if they have better data, better geometrical data for Bolund, or if we are going to work with a geometry that is wrong and that has already been proven to significantly affect the results, for me it doesn't make much sense. Perhaps there are newer geometrical data that I don't understand. And then I believe that once we are clear about the results, that we thought, or at least the WIN community thought, that we already had very good results for this case, and well, this paper on the devil is in the detail proves that all of the conclusions that we had obtained were incorrect. I remember that lots of people claim that RANS models work better than LES models for wind energy, and it is based partly on these results for Bolund, and I believe that it is important that this changes. This cannot be the case.
Thanks. There was there was another raised hand, so I want to give that person an opportunity. That was Xiaohu Gua. Please, you have your question.
Hello. Very nice. Thanks for the very nice presentation. I'd like to ask you a question about overset with Alya. So if you run really large scale simulation, what kind of performance profile when you're using overset?
I didn't get the question. Sorry.
So I saw you have mentioned about like a chamber-like overset methods using with Alya for the simulation with wind turbine.
Yeah, well, actually, it's not overset. There is no overlap. It's a sliding mesh approach, but well, for the parallel stuff, it's the same idea. So, which is the question now?
So when you're dealing with this, I'm wondering for the scale, when you investigate the scalability, what kind of major issue you for this kind of case? Is this going to be like a dynamic load balance issue, or is it going to like the main cost of being involved with sliding mesh or overset method?
No, here there is no dynamic load balancing. The mesh that is fixed is partitioned at the beginning, and the mesh that is rotating is also partitioned. But then the communications change each time the mesh rotates. And we have an algorithm that scales and that can work with this, and it doesn't introduce a significant overhead in the whole simulation. So going to big simulations doesn't seem to be a problem for this sliding mesh approach.
I think I have to. Thanks very much for the engagement and the question and the answer. So thanks very much, Hubert, for that. We need to move on to the next speaker. So I will now move on. So I hope